So today is lecture 5 of this course on basics of semiconductor, microwave and RF devices. So in the last two lectures we have basically covered about different kinds of RF device technologies that are there in the market today and the different applications and systems that they are used for. So now we have to actually start the core of the course. So from today, lecture 5, we will try to recap some of the basics of heterojunction physics, heterojunction transport. For the next few lectures we will recap heterojunction, then we will also give a brief overview of gallium nitride and polarization. Then we will move on to Schottky multipliers and varactors. That is the course content for this week. Okay. So this is week number 2 and we will have lectures from 5 to 10 covering these topics. Okay. So I will come to the whiteboard now. So today we shall try to recap some of the basics of heterojunction. The reason is heterojunction devices are some of the critical device technologies used in today's RF systems. For instance, gallium arsenide technology has gallium arsenide MESFET, gallium arsenide HEMT. Okay. There is also pseudomorphic HEMT based on this 3-5 family, okay, and then there is gallium nitride HEMT. These are some of the dominant technologies, and gallium nitride is also rapidly penetrating the market in both civilian and strategic sector RF systems. So it is very important for us to go through some of the basics of heterojunction. So most of this is already covered in basic semiconductor devices, but today we will try to recap in the context of RF devices, the basics for in the context of RF devices. So if we have two different materials, suppose this is a material with conduction band, okay, and there is suppose a valence band here, a conduction band valence band of two different material. So this is material 1, for instance this is material 2, and suppose this is your N type dope and this is your P type dope. If you join them together, how is the heterojunction look like? Okay, how does the energy band diagram look like? Now energy band diagram is a very important concept, because if you do not know how to draw energy band diagram of an arbitrary heterojunction, then you would not be able to understand the device. And if you know how to draw it but you do not draw it, then people will not understand what you are talking about. So we should be able to draw the heterojunction, and the basic rule of thumb here is that you think of it as an imaginary plane where both the heterojunctions are joining together, okay. And what you do is that, suppose I will take the black spot here, you fix this point where this conduction band is meeting, you fix this point where the valence band is meeting, okay. Then I will choose a different color, maybe I will choose the blue color. You fix this point where this conduction band is meeting, and you fix this point where the valence band is meeting. Now the conduction and valence band from both sides are pinned to these black and blue dots, so they will not move. However, what will happen here is that the Fermi level has to align in both cases. In equilibrium, the Fermi level EF has to remain constant. If the Fermi level has to remain constant, then this entire band will move down and this entire band will move up, so that the Fermi levels align. However, the black point will correspond to this and this, so when you move this up it will go like that, it will go like that, and when you are moving this down, okay, it will move like that and it will move like that until you have the Fermi levels aligned. So I can use the eraser here and I can probably erase this part, because the bands are no longer now flat, they will have to bend, okay. So I am basically erasing the straight parts, and the bands are bending now, you can see that. So they will bend, and eventually far away from the junction, the Fermi level and the difference between Fermi level and conduction band will not change on this side. So what I mean is that far away from the junction, the Fermi level and the conduction band gap, this gap will remain constant as before, and far away from the junction here, the valence band and the Fermi level difference on the other side also will remain same, but only near the interface they have basically this discontinuity that comes up. So the band looks like this, okay. Essentially what we do is that we push this side up and we push this side down, while the blue and the black spots were pinned, so that the conduction and valence band are basically fixed and then they are pushed up and down. So eventually what happens is that if I go to the next page, then it basically looks like you have a Fermi level, and then you have something like that, okay, and then you have the valence band coming up like that, okay, join here looks like that, okay, maybe join here looks like that, okay. So this is P type, this is N type, this is a wider band gap, this is a narrower band gap, this discontinuity is called delta EC, which it's conduction band discontinuity, and this is your delta EV, which is basically your valence band discontinuity. Okay. Now in this kind of heterojunction, the current flow, when you just look at IV characteristics, okay, in a PN junction, in a PN homojunction, we have the drift diffusion, where the current flows, the electrons from this side will be injected to the other side, holes from the p side will be injected to the n side, and then the minority carrier diffusion happens, except that in a heterojunction we have thermionic emission because there are barriers. Okay. For instance, there is this delta EC barrier across which the electrons have to go, okay, while the holes are injected from the p side to the n side. The total barrier that it sees is this. Okay, this is the barrier for holes, I will say delta phi h, and for electron this is the total barrier delta phi maybe electron. Okay. So this is the total barrier it overcomes. So essentially you have a thermionic emission because there are these abrupt discontinuities and the electrons and holes are injected across the barriers. So it is not just a normal drift diffusion equation, but actually this is more like a Schottky Schottky contact, and you can imagine that there is a thermionic emission of electrons or holes across a Schottky contact. Okay. So that is the basic thing that you need to keep in mind. So essentially what will happen is that if you take the ratio of the electron current to the hole current, if you take the ratio of the electron current to the hole current and you do some simple math here, typically in a PN junction what happens is that the ratio of electron current and hole current, so electron current is basically electrons going to the other side, hole current is the holes coming to this side. So the ratio of electron on hole current in typical PN junction is that this is your diffusion length of or diffusion coefficient of electron divided by diffusion coefficient of hole into the doping of electron divided by the doping of holes, the p type doping, the diffusion length of holes divided by diffusion length of electrons. Okay. This is your ratio of the electron current by hole current. What it means is that in a normal PN junction, in a homojunction, the ratio of electron and hole current can be only tuned by changing the doping, because your diffusion coefficients you cannot do much about it, the diffusion lengths are also you cannot do much about, only the thing that you can change is doping. But in a heterojunction you have an extra knob. Because of the way the band diagram looks like this, if you do a simple math, you will find out that the ratio of electron to hole current is not only this, but it is multiplied by the exponential of delta EV by KT, where delta EV is the valence band discontinuity here, delta EV, okay, and e to the power KT is the basically e to the power delta EV by KT. KT is your Boltzmann Boltzmann constant times temperature. So that is your thermal energy. So you see by essentially playing with the delta EV, you can change the electron to hole current ratio significantly. You can choose heterojunction, you can actually engineer the heterojunction such that you get a large delta EV, for instance. So even if this ratio is not so large, e to the power say delta EV is say 0.4 EV. So 0.4 divided by 0.026 will be almost e to the power maybe this is e to the power 15 or something. So that is a very large number. What it means is that your electron current and hole current ratio can be much larger than that is possible in a PN junction, and this is the beauty, one of the beauties of heterojunction. So you can manipulate this to your advantage in a device called HBT, heterojunction bipolar devices, which can give you far higher gain in a BJT or HBT beta. It can give you much higher beta without sacrificing the dope, without having to go for a very high doping, and still you can get very high current gain because you can engineer the beta based on the heterojunction discontinuity. Okay, so this is one of the very good things about heterojunction. You can selectively increase or decrease the electron and hole current, which is not possible otherwise in a normal PN junction. Okay, so that is something that we should keep in mind. Now if you look back at the, suppose I draw another heterojunction. Okay, suppose I have a heterojunction like this. Okay, so this is your Fermi level which is constant, and then you have something like this, okay, and then something like that. So this is n type of course, and then something like that, and then you have something like that. Okay, so this is p type and this is n type. This is your delta EV and this is your delta EC. Okay, so this band bending that is happening here, suppose I call it QV2. Okay, that is the band bending that is happening, and the band bending that is happening here far away from the junction, there is no field. Okay, this is a quasi neutral region. Okay, so there is no field here. The field only exists when the bands are bending. Okay, the fields exist only where the energy bands are bending. Okay. So, only when they are bending, for instance this, if I take the blue color for instance, I can tell you that this part is bending. So, there is a field here, this part is bending, there is a field here. So, these are conduction bands. So, there is a field for electrons, there is a field here because this is bending. So, there is a field for holes, this is bending, there is a field for holes. The valence band will correspond to holes and conduction band will correspond to electron in terms of transport. Okay. So, I will come back to again, maybe I will go back, I will choose a black color now. So, essentially what you are looking at this, what is the built in potential of this junction for instance. Okay. That is a very important built in voltage you can say, or built in potential. Okay. So, a built in potential of a PN junction is very easy to calculate, because you just go from one side to another side. And so, what I am trying to say is that if you have a junction like that in a homojunction, this is your built in voltage, I call it QVBI. From this part to this part, what is the potential drop. Okay. So, same thing here, same QVBI, but in a heterojunction it is not that simple. So, what you have to do is that you have to basically first, there is a doping here, say Na, okay, and this is called Na2 because it is on the second, this is the second semiconductor, and this is a doping of N side, Nd, it is the N type doping Nd1. Okay. So, this gap between the Fermi level and the valence band on the neutral side, okay, that gap is basically given by kT by q ln of, okay, ln of N V2 divided by Na2, where Nv is the valence band effective density of states. Okay. These are known from your basic semiconductor device class. Okay. So, effective density of states in the valence band Nv2, it is a material property and it is provided to you, or you can find it out if you know the effective mass, and Na2 is the doping of the semiconductor. So, this quantity is known. If you know the doping and the effective mass of which is provided typically, then you know the EF minus EV on this side. Similarly, the EC minus this gap, the EC minus EF on the N side is given by kT by q into ln NC1, which is basically your effective density of mass, effective density of states of the electrons in the band gap, this is the first band gap semiconductor here, divided by Nd1. Nd1 is the doping. So, you know that quantity too. Now, the way to go about finding out the built in potential of this kind of a heterojunction is that I will draw it again. Suppose this is your Fermi level, okay, and you have something like that. Okay, you have something like that, and I know that this band bending is suppose QV2, this band bending is QV1. Okay, then I will take the red color here, this is delta EC, this is delta EV. Okay. What I do is that I start from the Fermi level and I go up by this quantity, then I go up by this quantity. So, I reach this point. Okay. Then I go down by this quantity, or I can go down by the entire band gap here, the entire band gap, and then I again come up by this quantity. Okay. Then I can come back up by this quantity and I will be at the Fermi level again. Okay. I can come up the Fermi level again. See, the thing is that the top of the conduction band here does not necessarily have to coincide with this level here. What I mean is that this is the way I draw, but I had drawn, but it need not be that way. What I mean is that suppose this is a Fermi level, okay, and suppose I choose the black color here. What I mean is that it can go like that, it can be like that, okay, and then it can go like that. The band gap is not changing, my drawing might be little bit off, it go like that. Okay. So, essentially this spacing I know, this energy gap I know, this is QV2, this is QV1. Okay. Then I choose the red color again, this is your delta EC, this is your delta EV. Okay. So, I start from the Fermi level here. So, maybe I will take the blue color now. Okay. So, I start from the Fermi level here, I go up by this quantity. So, what is that quantity? That quantity is, if you recall, kT by q ln Nc1 by Nd1. Nd1 is the doping on this side, Na2 is the doping on that side, NC1 is the effective conduction band density of states on this side. Okay, we know these numbers. I go up by that quantity, I go still up by this quantity, which is plus QV1. Okay, that's your entire band bending that's happening. I don't know what it is, but that's the band bending. Now I come down by the conduction band, I come down here. Okay, I come down by conduction band, so that's minus delta EC. I come down. Okay, maybe I'll just if I'm putting everything as voltage, then maybe I will have to erase this Q here. Okay, because I'm putting everything as voltage, then this will be by Q. Okay, so I come down by this, so I'm at this point now. Now I'll move up again by this quantity. Okay, I'll move up again by this quantity, so I reach here this point. So I'll move up by QV2 plus QV2. Now I'm at this point, I'll come down by the entire band gap, and the band gap is EG2. This is band gap is EG1. So I'll come down by that. So minus EG2 by Q. So I'll remove this Q again. Sorry, where is that eraser? Is here. So I'll remove this Q here. Okay, just V2 here. Okay, sorry, minus EG. I'm coming here, and then I'll go up by again this quantity, which is plus KT by Q ln NV2 by Na2. So I'm again at the Fermi level. So I started from here and I ended up here. So the Fermi level to Fermi level difference is 0. So I can put this equal to 0. Okay, this is equal to 0. Now what does it mean is that your built-in potential, okay, your built-in potential is basically V1 plus V2, which is the band bending here. How much is the band bending on the N side plus how much is the band bending on the P side. Okay, so the band bending on both sides, you add them up together. Okay, so this is the band bending on this side, this is the band bending on this side, this is the band bending on the other side. Okay, how much is the band bending? You add them both, which is basically V1 plus V2. Okay, this plus that. So that is band bending. So I can take this, I can keep this here and move everything else. So this is your actually built-in potential. Okay, the band bending on both sides added together is your built-in potential, is equal to, I take everything on the other side. So it's delta EC by Q plus delta EG by 2, delta EG, that delta EG actually by Q, okay, minus this quantity, I call it maybe psi 2, minus this quantity minus psi 1. Okay, I call it minus psi 1 and psi 2. Okay, so essentially this is equal to delta EC. Actually not, this is not delta EG, this is delta EG, this is EG only, because that is the entire band gap, plus EG by Q minus psi 1 plus psi 2. Okay, so this is your built-in potential of a heterojunction. Okay, so any heterojunction you are given, you have to approach that like you have to start from the Fermi level, go and loop around it, come back to the Fermi level, you add and subtract whatever potentials are there, and finally you find out the total band bending on both sides, you get the built-in potential. So this is how built-in potential is found out. And for a PN junction such as this, you have to understand that if you draw an electric field profile, for instance, typically if you plot the electric field profile, it's a triangle in a PN junction, something like that. This is your minus maybe the depletion length on the electron N side, this is the depletion length on the P side, but here what happens is that because the dielectric constants are different, this is your dielectric constant 1, this is your dielectric constant 2, and the dielectric constants could be very different. Across this junction, what is continuous is the product of dielectric constant time field, it's called the displacement vector. Okay, so the displacement vector across the interface is constant, so the product of electric field and the dielectric constant is a constant. So what it means is that this was a homojunction. But if I come to a heterojunction, then what it means is that depending on the dielectric constant, your diagram might look something like, say, this is one thing and the other might look like this. So this is 0, this is maybe depletion on the N side, this is depletion on the P side. The peak electric field could be different, but the product of the dielectric constant and the peak electric field at this junction should be constant. Okay, so this could be your electric field 1, this could be peak electric field 2, and the electric field linearly decreases. Of course, there is a depletion on this side, there is a depletion on the other side, and so your total depletion width, which is Wn by Wp, has to be modified to accommodate this fact that there are two different dielectric constants. Okay, and if you find out the area under this two triangle at equilibrium, equilibrium means that there is no voltage applied, there is no magnetic field, no light shining, nothing else. So in equilibrium, the area under this triangle, basically which is your half into Wn into F1 plus half into Wp into F2, this is your total built-in potential. Okay, the built-in potential is the area under the two triangles added together. Okay. So this is about the band diagram of heterojunction. The current flow I already talked about, and this is the electric field profile. I talked about the built-in potential. Okay. So this is an important basically type of a revision, so that it helps you try to recap some of the basics of heterojunction device physics that people usually learn in some basic semiconductor device courses. Okay. Now an interesting thing of heterojunction is that whatever we have discussed so far is called an abrupt heterojunction, because there is something abrupt about here, something like that. It's an abrupt junction, right? It's an abrupt junction. This junction is very abrupt. Okay. But there is also something called graded heterojunction, and graded heterojunction is also very important, very interesting for RF devices. Okay. For instance, what it means is that when I talk about these different materials, say material 1 and material 2, we have to take a step back, and now we have to go, before I talk about graded heterojunction, we have to delve into the topic of a bit of materials. Okay. Because all these devices are built on materials, so it is very, very important that we have a recap of some of the material science concepts before we talk about heterojunction, because the way to realize a practical heterojunction is to engineer the material, is to grow or deposit the material atomic layer by atomic layer, so that you can have such heterojunction. So a basic background on the materials required for this kind of junction is essential at this point in time. So the first thing about such the material is that you cannot arbitrarily form a heterojunction between two arbitrary material. Okay. Cannot arbitrarily form a heterojunction between any two material, Okay. You cannot just put, there has to be certain condition. For what I mean is that, suppose I take a material called say indium antimonide. It's a very low band gap material. Indium antimonide is a compound semiconductor. Compound semiconductor means that there are two material here, two elements, indium and antimony. So it's indium's antimonide. Silicon is not a compound semiconductor, or a germanium is not a compound semiconductor, because it's an elemental semiconductor. There is only one element here. Now whenever you form heterojunction, the way to form is that the material that you form, suppose this is your material 1, which you are forming on top of material 2. Okay. So material 1 on top of material 2. You cannot arbitrarily form a heterojunction between material 1 and material 2 in the conventional sense where you can make an RF device. Okay. The heterojunction needs to be epitaxial. What it means is that the crystal structure of the layer 1 has to mimic the crystal structure of the layer 2. They have to be of the same crystal structure or crystal family, and they should be able to mimic the structure below. The one should be able to mimic the structure below of the substrate below 2, okay, of the substrate which is 2, which means if you have a silicon wafer, you cannot arbitrarily grow indium antimonide on top of silicon. Okay. It will not grow. It will not grow uniformly, it will not grow planar, it could be islands, it could be hillocks, it will not be a planar uniform film. You need a planar uniform film, okay, uniform film or uniform layer, which is also crystalline, okay, which is also crystalline, for actually making good RF devices that can go into production, that can be mass produced, that are reliable, robust, consistent. Okay. There's all kinds of research of course on making nano islands, different kind of island growths, etc. They could be useful for other device applications, but typically for RF devices you need a crystalline film. Crystalline film means that all the atoms have the same arrangement in the crystal. You do not have different orientations and different arrangement of atoms in a crystal. Okay. So if you have different arrangement of atoms in a crystal, it's amorphous. If you have grains of similar arrangement and these grains are of course different oriented, then they are polycrystalline. A crystalline has uniform and the same arrangement of atoms in the entire crystal. Okay. And you know about different kinds of, we talk about FCC, BCC, there are different kind of ways the atoms are arranged. There could be a hexagonal, for instance, lattice, a hexagonal crystal lattice, there could be Woodside, there could be zinc blende, there could be different arrangement in schemes in which the atoms are arranged. And so when you grow one material on top of another, they have to be of the same family of the crystals compounds, and they need to mimic the crystal structure below, which means you cannot arbitrarily grow or deposit one material on top of another, it will just not grow. Okay? The kinetics and the thermodynamics will not allow you to grow a planar uniform crystalline film if you arbitrarily grow, for instance, indium arsenide on top of say aluminum nitride. These are two different semiconductors, you cannot arbitrarily grow that. Okay. So, typically compound semiconductors have been historically 3-5 semiconductors, which means there is gallium, there is aluminum, there is indium, okay, or maybe I had written it down in the wrong way, it is aluminum, then gallium, then indium, and on the group 5 there is let me erase this, okay, on the group 5 there is arsenic, there is phosphorus. Of course, there is also other groups like antimony and other things. I am not coming to that because predominantly it is this family that you can mix and match the alloys here. So, you can have aluminum arsenide, aluminum phosphide, gallium arsenide, gallium phosphide, indium arsenide, indium phosphide, and then you can mix and match the alloys. You can have indium aluminum arsenide, okay, or you can have gallium indium phosphide, for instance. You can have different materials, and how would you make sure that you can form a heterojunction? They are all from the same 3-5 family, and so they can mimic the crystal structure below. So, they can mimic the crystal structure below, so you can actually grow them. But the point number 2 that this is the point number 1, the point number 2 that I am coming to is that there is something called lattice mismatch, okay. Lattice mismatch, which means lattice mismatch basically means that when you have a material, suppose you have these atoms are, this is the atomic arrangement of a material, okay, this is the atomic arrangement. I am just drawing a 2-dimensional simple schematic. So, the spacing between two atoms is called say A, okay, just suppose I am calling it A. Now, this is suppose your gallium arsenide, okay. Now, on top of that I want to deposit indium phosphide or maybe some other compound of indium gallium phosphide or something, and that material suppose have, I will draw a red color here maybe, okay. Suppose this is the atomic arrangement, okay. What you can see is that the spacing between two atoms here is suppose A naught. You can very well see that A naught is less than A, which means there is a mismatch in the lattice constant. So, this A or A naught is called lattice constant, okay, lattice constant. So, the lattice constants of the top material is different from the lattice constant of the material below. So, if you try to deposit material this on top of the material, the black one, okay, then the thing is that this layer has to be stretched out, pulled out, so that you think of this like a spring. You have a spring like this, you are pulling it out so that the gap increases and it can match the spacing below here. You are pulling it up so that it can match the spacing below. Essentially, the top layer you are stretching outwards such that like a spring ball, this spacing increases so that you are accommodating or you can exactly mimic the structure below. This is called a tensile stress of the layer on the top or a tensile strain of the layer on the top, okay. And this tensile stress or strain cannot be arbitrarily high, otherwise the film will crack, the top film will crack because it can no longer accommodate that strain energy that is building up inside the material due to the fact that you are pulling it out to grow it on the material below, okay. You are not physically pulling it, the material itself will pull out in order to mimic the crystal structure below. This is called tensile stress, and there is a limit to the number of layers you can grow or the thickness. The total thickness of the material you can grow has a limit, otherwise it will crack. The best thing is that you do not have this mismatch, in which case you can grow arbitrarily thick. Now, if you have this kind of mismatches, then there will be missing line of atoms in between because they are mismatched, although they are of the same crystal family, and so there is no problem with the mimicking the structure below, but because the lattice constants are not the same, there will be dislocations. Dislocations are basically missing line of atoms that will originate at the interface of these two material because they are not of the same lattice constant, and those dislocations are basically extended defects. The missing line of atoms are actually extended defects called dislocations, which adversely affect the device performance. They adversely affect the device performance. So, you do not want such lattice mismatch. The opposite of that is compressive stress. Opposite of tensile is compressive stress, which is that the lattice constant is much larger. What I mean is that if you have a lattice constant here like that, the layer that you are growing on the top, if I use a blue color, has a lattice constant something like that. So to mimic it, you have to push it inward. So there is a stress coming in from his side, you are squeezing it up the spring ball so that they can mimic the structure below. This is called compressive stress. Compressive stress also will lead to missing line of atoms or dislocation. So typically in compound semiconductor like 3,5 gallium arsenide indium phosphide family, people try to exactly match the lattice constant A equal to A naught, so that there is no strain that is generated, so there is no dislocation that will come. So the material quality is very good if there is no dislocation. The device performance is not adversely affected, and you can grow very thick layers also without cracking. So people do that by looking at a chart, a very famous chart. So in that you can find it in any research group, or you can even in Google you can find out. On the y axis is basically the band gap of different material. On the x axis is the lattice constant. Lattice constant is in angstrom. 1 angstrom is 0.1 nanometer. The electron the band gap is in electron volt eV here. So for instance, gallium arsenide could be here, okay, indium arsenide could be here, and this goes like that. So if you go from gallium arsenide to indium arsenide, the band gap will change like that. Okay, indium phosphide could be here, for instance, just telling you an example. What this line means is that when you have indium gallium arsenide, it's a ternary alloy. A ternary alloy means that there are 3 elements, indium, gallium and arsenic. Okay, so the fraction of indium that you are using, say I am using 20%, so 0.2, then gallium will be naturally 0.8. So people what they write is that x, and this is 1 minus x, that is the mole fraction. So x fraction of indium arsenide is mixed with 1 minus x fraction of gallium arsenide, okay, and this is grown by these techniques called MBE or MOCVD, metal organic chemical vapor deposition, or molecular beam epitaxy, in which you can grow these layers 1 atomic layer at a time. You can grow at 1 atomic layer at a time. So the precision is at the level of 1 atomic layer, and that is how you actually get heterojunction, and that is how which enable you to make these high speed HEMT transistors which find application in RF devices. So the whole thing is fairly involved. It is not a very simple game, the entire thing from material to device to circuit to system is a fairly convoluted game. You need to understand right from the basics here to actually appreciate the device, in turn to appreciate the power amplifier or the system that is being built. Okay, so here what is happening here is that this means if you go from gallium arsenide to indium arsenide, the band gap goes like that. So if you have say 30% gallium arsenide and say maybe 70% indium arsenide, you are here. If you have 60% gallium arsenide and 40% indium arsenide, maybe you are here. So something like that. So you can see that when it reaches these points, for instance, it exactly matches the same lattice constant here. Okay, so I can choose this in gas, whatever that composition is, okay, x 1 minus x, and it will be lattice matched to indium phosphide because they are on the same line. Similarly, there could be gallium phosphide here. So gallium phosphide, indium phosphide has a band like that. So if I keep pushing some amount of gallium phosphide and some amount of indium phosphide, maybe they will come here, say 40, 60 or something like that, and that's exactly at the lattice constant here, A naught or whatever, is the same as that of gallium arsenide. So indium gallium phosphide of certain composition is matched to gallium arsenide. So you can find out what composition is that, and you can grow indium gallium phosphide of that composition. You can check that what composition is with respect to gallium arsenide, and they could be say perfectly lattice matched. Okay, they could be perfectly lattice matched, and that's a very nice thing, because now you actually do not generate any dislocation because the atomic spacing on both these layers are identical. Okay, that's how you do the lattice engineering, and that's how you decide what heterostructure to grow. So the next time you think of a heterojunction, you remember that you cannot arbitrarily grow say germanium on top of gallium arsenide or gallium nitride. Okay, it's not just possible. First of all, your crystal structures have to be similar, of the same family, and secondly, their lattice mismatch should be minimal, or you should either completely remove lattice mismatch or it should be minimal. In which case, if it is minimal, you cannot still grow very thick, otherwise it will relax and create a lot of dislocation. So you do not want it to relax, otherwise it will release dislocation. So now that we know about this, now we can actually go back to the graded heterojunction concept. Okay, now we can go back to graded heterojunction concept. So what I mean by graded heterojunction is that suppose I have aluminum arsenide. Okay, this is aluminum arsenide, and suppose this is gallium arsenide. Okay, this is a band gap of gallium arsenide which is say 1.4 electron volt. Aluminum arsenide could be say 2.1 or 2.2 electron volt, something like that. I don't exactly remember, it's air 2.1 to 2.2. So if you form a heterojunction, of course it will be an abrupt heterojunction, but while coming from gallium arsenide to aluminum arsenide, if I continuously change the mole fraction of gallium arsenide, and what I mean is that I start incorporating aluminum arsenide slowly. Okay, so this is 0% aluminum arsenide and 100% gallium arsenide. This is 0% gallium arsenide and this is 100% aluminum arsenide. Now I slowly start to increase the aluminum arsenide to 1% and gallium arsenide to 99%, like that. Okay, then I make it 2% gallium arsenide, 98%, oh sorry, 2% aluminum arsenide, 98% gallium arsenide. I keep doing that. So what will happen is that continuously, and this is x axis is distance in micrometer or nanometer. So as I keep doing that, the band gap will keep increasing. Okay, continuously it will increase and it will eventually see like that. So the band gap, this is band gap, continuously increases, continuously changes. So you can say increases in this case, but it is continuously changing. If I am looking from this side, the band gap is continuously decreasing. If I look from this side, the band gap is continuously increasing. So the band gap is continuously increasing and eventually it is meeting up with aluminum arsenide. So this junction is called a graded junction because there is no abrupt like that. It's a graded junction. So it has a smooth transition. I'm gradually changing the mole fraction of aluminum arsenide and gallium arsenide such that it's a smooth transition from one to another. The band gap is continuously changing. Okay, the band gap is continuously changing and this can be done by MBE or MOCVD, where one atomic layer at a time you can change. So you can choose to incorporate more aluminum arsenide layer by layer. So in one layer I give aluminum arsenide 10%, the next time I give 11%, 12%, etc. I can keep changing so that over a certain distance the band gap continuously changes. So it will look something like that. Suppose this is, I'm just overblowing and exaggerating the whole thing. This is gallium arsenide, this is aluminum arsenide. So this is your graded junction. This is your graded junction where you do not have any abruptness, no abruptness. Okay, no abruptness is there. Okay, so this is a graded heterojunction and this is very interesting because when the band gap is continuously decreasing, you see the band is bending like this. Okay, let me choose the blue color maybe. So if an electron is here, it will roll downhill this way, correct. So the electric field is in this direction. For the conduction band, for electrons, the electric field is like that. But if I have a hole here, okay, if I have a hole here, what will happen? If I have a hole here, the hole will also roll downhill like that. Okay, which means the electric field for hole is like that. So essentially what is happening is that, wait 1 second, sorry, if I have an electron that goes downhill like that, then the electric field is in this direction. Hole, this is your p type semiconductor, this is your n type semiconductor. So the hole will roll downhill actually like that. I'm so sorry here. Okay, the hole will actually roll downhill. So the electric field is in this direction, opposite direction, in a normal homojunction. In a normal homojunction of silicon p-n diode, the electrons will roll downhill this way. So the electric field is in this direction. The hole will roll downhill like that. So the electric field for hole is in this direction. Typically what happens is that the electric field and for electrons and holes are in this opposite direction. But here, you know, I can actually engineer, because the band gap is continuously decreasing like that. The band gap is continuously decreasing like that. Okay. So what will happen here is that the holes will try to move in this direction, which means the electric field is in this direction. So I can actually have electric field for electrons and holes in opposite direction or in the same direction. Okay, and I can change their magnitude because the valence band and the conduction band can be tailored separately. With this graded scheme, I can actually because the conduction band typically bends like that and valence band also bends like that in a homojunction. In a graded heterojunction, the conduction band can bend like that and valence band can bend like that. So you can see that the band gap that is continuously decreasing can actually give this slope here gives you the electric field for only electron, and the slope here gives you the electric field for only holes. So the magnitude as well as the direction of electric field for electrons and holes can be separately engineered in a heterojunction, in a graded heterojunction, which is not possible in a homojunction. And this is the reason why heterojunctions give you an extra degree of freedom to play with, because you can have different magnitude of electric and fields for electrons and holes, different direction, and this is not ideally possible in a silicon or a germanium homojunction. Okay. So this is one of the very good things about heterojunction, it gives you an extra degree of freedom. So this is abrupt, this is graded heterojunction. We already talked about abrupt heterojunction. Okay. So this is we will come to the end of lecture 5 here today. So in lecture 5 essentially we introduced the basic concept of heterojunction physics. We talked about electron transport, we talked about built-in voltage, the basic band diagram, the electric field diagram. We had a very brief tour of the material science fundamentals in terms of lattice mismatch, crystal growth, MBE, MOCVD, and we did not go into the details of MBE, MOCVD, but those are the techniques that people employ to grow this heterojunction with abrupt interfaces. And then we concluded this lecture by going through graded heterojunction, where you can manipulate the electric field for electrons and holes separately when you continuously change the band gap of a material by grading the composition of the alloy. Okay. So this alloy composition can be graded over a certain distance. So this brings us to the conclusion of lecture 5. In the next lecture, lecture 6, we will wrap up some of the things of heterojunction and we will start about the basics of gallium nitride alloys and gallium nitride polarization, which is important to understand the concept of a high electron mobility transistor for gallium nitride. Okay. So thank you everyone, we will meet at lecture 6 in the next class. Thank you.